So, chapter 1 is called Atoms. What exactly are atoms? Well, atoms are the components of matter, and matter is all the stuff around us. Last Christmas, I got a shirt from my family that says, "Don't trust an atom. They make up everything," and that is to be taken literally. Atoms are the building blocks of all of matter and everything around it. So this picture here is an image of a retired Walt Disney or Disneyland ride called Adventure Through Inner Space. And so it's this ride where you are led to believe that you are being shrunk tinier than an atom, and you go into this inner space or this miniature world. And I haven't been on it, but I read that you at first you are being shrunk. Well, you're not really being shrunk, but there's this large snowflake, and then as you proceed on this ride, the snowflakes get larger and larger, giving you the impression that you're shrinking, and then at some point you end up looking at atoms, and so you see the snowflakes here, and then you're inside of the snowflake, which is of course made up of water. And so most of you know that water is made up of oxygen and hydrogen, 2 parts hydrogen, and that's what you see here. Here's hydrogen, and the red atom here is oxygen. But so this entire chapter is about atoms and scientific experimentation. It's just to introduce you to the subject matter. Now, okay, so I'm sure everyone has asked themselves a scientific question like, why do helium balloons go up? Or why does water boil? Right? So maybe you even have conducted an experiment that you designed yourself. When you were a toddler, for example, most kids play in the bathtub with toys, and then maybe you've observed that some toys float and some toys sink, and so based on that, you conducted an experiment. You got all your toys and you threw them in the bathtub, and you observed, right? And so that's what a scientific experiment is. Maybe not designed by a toddler, but well, yes, you could. As long as there is an observation and you ask yourself a question, you can design an experiment, carry it out in a controlled manner, and then maybe you can come up with a hypothesis, right? So a hypothesis could be that you notice that certain types of toys float, and it's based on the material, like wood. Wood floats, and of course, as you know from chapter E, this is based on the mass over volume ratio, and then you have to take this a little further. Is this true for all material? Wood will always float, so then your theory becomes, at some point, if you've tested this enough on many wooden blocks, and it's repeatable, so then you might come to the theory, you derive at the theory, wood will always float on water due to its low mass to volume ratio. This is independent of the size or the quantity. And you may even be able to derive a law where you can calculate, you can then measure the mass and the volume of water, and you can derive with a law where you say density equals mass over volume, and that becomes an intrinsic property of matter independent of its quantity. And so then that's a pretty strong, it has grown from an observation through an experiment to a hypothesis, into a theory, and then into a law. And that's how the scientific process works. One of the important laws of chemistry, or laws of physics, matter, is the law of conservation of mass. And it states the total mass remains constant during a chemical change, and that's true. So you start with 50 grams of something, you end up with 50 grams of something, even if you don't observe that, right? If you burn a piece of wood and you don't see that some of the products go off into air, they're carbon dioxide and water, and they usually are in the gas phase. So what's left over is less than 50 grams if you burn 50 grams of wood. But it's not true. You do end up with 50 grams. It's just not the same stuff. It's different. So we have to make some definitions here. Mass and matter. Matter is whatever occupies space and can be perceived by our senses. Anything that occupies space is probably a better definition. You can hear music that's perceived by your senses. Music is not necessarily matter, right? And then mass is the quantity of matter in a material, and volume, which is not listed here, is how much space matter occupies. That's the volume, all right? Okay, so here we have an example. Very simple example. So if you have carbon and oxygen, and you combine them to make carbon dioxide, if you have 12 grams of carbon and 32 grams of oxygen, it's always going to be in that ratio. Okay, it's also additive here, right? So 12 and 32 is 44 grams. If you start out with 44 grams, you end up with 44 grams. And so if you divide this by 4, right, you end up with the ratio, which is 3 to 8 to 11. So carbon dioxide is always going to be composed in a 3 to 8 ratio of carbon to oxygen. And then you can actually, based on that observation and determination, you can then figure out if 7 grams of carbon dioxide react, or if carbon react to form 25.7 grams, you can then backtrack. Obviously, you can just say, okay, if I have 25.7 grams produced and I had 7 grams of oxygen, then I am missing 18.7 grams of oxygen, right? So that must be here, what's missing here, the 18.7, because of the law of conservation of mass, right? You can actually, if you spend a few minutes looking at that and this 3 to 8 to 11 ratio, you can come up with conversion factors. You can just then simply say that 12 grams of carbon are always equal to 32 grams of oxygen. Okay, that becomes a conversion factor. And so you can then calculate that if you have 7 grams of carbon, and you then set this up as a conversion factor, so you divide by 12 grams of carbon and you multiply by 32 grams of oxygen, you actually come up with that 18.7 grams of oxygen, because you know this ratio is always the same. You don't have to change that to 3 grams equals to 8 grams. So just by looking at this logically, you can predict, and you don't need to know, you can predict also how much carbon dioxide will be produced. But the units are canceling, and that's exactly what goes well. If it was for the 7 plus 18.7, that would go in there. This is another example. This is one of the experiments that Lavoisier designed in the 1700s. He recognized and named oxygen back in 1778, right? So he took, for example, mercury oxide, which has this beautiful red color, and so he heats it up in a test tube, and it turns into this is almost like alchemy, right? You think you're turning a red solid into silver beads, but it's a reduction reaction that produces that decomposition reaction that produces mercury and oxygen gas. Of course, that oxygen goes away, and what he did, he heated this up in a test tube with a Bunsen burner, and connected the test tube to sealed the test tube, connected it to a tube, and put the tube into water, and he observed there were some bubbles, so he knew that there was some other matter that was given off, and he burned all kinds of things and weighed them before and after, and collected different kinds of gases and tested these gases, like if you hold a candle to the gas you collected from this particular reaction, oxygen, for example, that you would feed, of course, the combustion with oxygen, and the light would burn more. Or if you produced nitrogen and you tested that would take out the light, for example, the candle. So this is just one of hundreds of experiments that scientists conducted, and Lavoisier, a French scientist, was given credit for a lot of these discoveries. All right, we're going to shift gears just slightly. We're going to look into, we just saw a reaction where we took a solid and turned it into partially a gas, right? So we have different states of matter. Matter can be liquid, solid, and gaseous. And so they have different properties depending, and you can turn, you can go from, as you know, you can turn ice, which is liquid, which is solid water. You can turn that by heating it. You can turn it into a liquid, and then if you heat it more, if you boil it, you can turn it into a gas, right? So you can, this is called a phase change, right? You can go from solid to liquid to gas by sticking heat into it, and you can reverse that process. You can condense that gas by cooling it off or removing heat from a particular system, right? And so solids are rigid. The molecules or atoms are packed very tightly. They have a fixed shape and volume, right? You cannot really take it apart very easily, whereas a liquid takes up the shape of the container, right? If I have a liquid in a coffee cup where I can pour it out on the table, it'll go all over the place. So it doesn't have a fixed shape, but it has a fixed volume, okay? And it's also not very compressible. You can neither compress solids nor liquids. The only difference is that the molecules are held together, or atoms are held together a little looser. That's all it is. But in the gas phase, you actually are taking these atoms and they no longer stick to each other, right? In the solid and the liquid, they're packed fairly tightly. In gas, they do not stick to each other anymore, okay? So a gas, but you can compress a gas, and so that's actually pretty simple and illustrated here in this picture. On the left, we have a solid. The molecules in this solid are packed very tightly, and so if you put a weight on it, you're really not going to change its volume. Whereas a gas, the atoms are spread out, or in this case, they're molecules. It's a molecule because you have more than one atom. And if you just had a single element or a single atom, then that's no longer a molecule. Anyway, so you can compress that because they're far apart, and so you can put a weight on there. This is just to show you. This is a summary slide, a closer look on how tightly these atoms are packed in the solid, very arranged, and then as you heat this up, they become liquid, or can become liquid, and so then they're mobile, but they still stick to each other. There's still so-called intermolecular interactions, and so then that interaction is broken in the gas phase, and they go far apart, and so it becomes compressible. Okay, so here's 2 slides of definitions. I'm going to skip to a chart real quick, but I'm going to, of course you have access to the slides, but I'm going to go over all of these definitions. All right, so all of matter is made up of stuff, of course, and we can differentiate that. If we have pure substances, they're either elements or compound, right? So substances is a kind of matter that cannot be separated into other kinds of matter, right? So in that case, you either have an element or a compound, right? And so elements is a substance that cannot be decomposed by a chemical reaction into simpler substances, right? So oxygen is just going to be oxygen. If you break it further, it's no longer oxygen. So that would be, or helium here in this case. And a compound is made up of 2 or more atoms in a particular ratio, right? So as is illustrated here in this picture, you have water molecules in this glass of water. And then if you have mixtures, you either have heterogeneous or homogeneous mixtures. So first of all, a mixture either contains 2 or more elements, or 2 or more compounds or molecules, right? Or elements and molecules together, right? So here we have the example of wet sand. Either way you look at it, you can look at ocean water. Ocean water is made up of water and Oh, never mind. See, they're doing the heterogeneous example here, right? So I'm still just talking about mixtures, right? But heterogeneous mixture means that you can tell the individual components, right? And so sand, if you get close up to it, you can see different types of grains, maybe even different kinds of minerals, so you know it's a mixture. You can visually tell that that's a mixture. Whereas if you have a glass of water, if you poured and filtered that ocean water, for example, right? For you to visually distinguish between this cup and the ocean water in a cup might be kind of hard unless the ocean water is somehow colored, right? But if it is, but it's going to be homogeneous, and you know you have sodium chloride dissolved and maybe other minerals, right? So just like this tea, you can tell here that this is not water, so you can assume that it is a homogeneous mixture because you see the color and you know that water is colorless. Anyway, these are just different definitions. They're all on the slides that precede this slide. Okay, so let's look at some more examples of heterogeneous mixtures, right? As salad or sand and water together, you can tell the two. That's pretty easy. Raisin bran cereals are for the most part. And anyway, it's a mixture where you can visually tell. Homogeneous mixtures, you cannot visually tell or distinguish them between elements and homogeneous mixture, right? You can only use your common sense. For example, air. If you look outside through a window, you're looking through air. You cannot tell the individual components, but you should know that we have not just oxygen. In fact, oxygen is a minor component. The major component is actually nitrogen, and then oxygen with carbon dioxide, argon, and other types of gases. So that's a mixture. Or salt water, like the ocean water on the other page. Phases is just solid, liquid, and just as shown here, solid, liquid, and gas. And if I say we undergo a phase change, that means we're going from one form to another. We're either going from solid to liquid. So here you can melt. Going this way is melting. Going this way is freezing. And if you heat up a liquid, that's condensation. Sorry, that's evaporation, of course. And if you go the other way around, that's condensation. And there are actually phase changes. Certain matter, ice, for example, can do that. If you heat ice and keep the outside temperature cold, you can actually sublime it, right? So you can actually go from solid to, you can have a phase change from solid to gas, and that's called sublimation. But that's not the focus. It's just of this particular talk. Anyway, we have a few more definitions here, or summaries of some sort. Physical change and chemical change. Is a difference here, of course. If you undergo a physical change, you're basically just doing most of the time it's going to be a phase change, like melting and freezing and condensation. But it can also be cutting up something into smaller pieces, right? You take a sheet of paper, that's just a physical change. You're just cutting it into smaller pieces. You haven't changed anything chemically, right? So liquid converting to gas, and sugar. Oh, there's another great example where it's not a phase change. You're taking sugar and you are dissolving it in water. That's a physical change. A chemical change, on the other hand, changes the matter. Okay, it turns one element. It doesn't turn an element. It turns a molecule and rips it apart and combines it differently. Or in the example of Lavoisier mercury oxide, it decomposed it. It took that mercury oxide, which was combined, and ripped it apart and decomposed it into its elements. Okay, and so a chemical property is a characteristic of material involving its chemical change, right? Like, is something combustible? Does something corrode? You can take glass and it will not corrode. You can put acid into a glass, and so that means it's inert. The chemical property of glass, it does not react with acid, whereas the chemical property of something else is it does react with acid. For example, iron will corrode or react with acid. Or is it combustible? Does it burn? You can't burn glass, but you can burn wood. So those are just two different examples. Okay, so this is lecture 1, and you can go on to the next lecture if you like.